Hello and welcome again to the Evergreen Building at the College of Southern Idaho in Twin Falls, Idaho. This is my classroom here at the college. My name is Shawn Willsey, geology professor here, and we're going to continue with our series on looking at different types of sedimentary rocks. It would be a good idea, if you haven't already, to make sure you've looked at the introduction to sedimentary rocks so that everything we present today and in subsequent videos makes a little bit more sense and you have the context for it. Before we get started, I want to encourage folks to continue to like, share, and subscribe if you enjoy the videos and the content I put together. A couple of different ways if you feel compelled to donate to the channel, ways you can do that. There's a donate button on the banner of the YouTube channel. Underneath every video description, there's also a PayPal link, some information on Venmo. And then there's this other feature I just became aware of. If you there should be 3 little dots next to the video description. If you click on one of those, there's this thing called Super Thanks, and it's another way to donate if you like the content. So let's go ahead and get started here, as we normally do, with kind of getting into some of the notes and some of the the topic, if you will. And these notes are always going to be linked to a PDF underneath the video description, so you can always look these up and print them out or do with them what you will. So we're going to focus today on 3 clastic sedimentary rocks: Conglomerate, Breccia, and Diamictite. I'll grab a pen here so I can point out a few things. So these 3 rocks here, and these are probably the 2 you've heard of mostly. We'll get to this one a little bit later, Diamictite. But these rocks are all part of our clastic sedimentary rocks. Remember, clastic sedimentary rocks are sedimentary rocks made out of broken rock fragments. And in this case, this group of rocks here, the clastic sedimentary rocks we're looking at, these are all rocks that have large size particles. So gravel size particles, bigger than 2 millimeters, so bigger than let's say a BB or so. And then that gravel is going to be surrounded with variable amounts of finer grained material, and that could range from sand to mud. The important thing to think about here, and we talk about the story behind these rocks, which is really the most important thing, is because we have such large particles in these rocks, that indicates that the environment, the setting, or the process that deposited those gravels had to be a fairly high energy type of system, meaning there had to be sufficient amount of moving water or glacial ice or wind or whatever the mechanism is. We need some environment that can transport large particles. Because again, we're going to be looking at rocks here that have large particles, large broken rock fragments embedded in them. And so we need some sort of process that can account for the transportation and deposition of particles of that size. So something to keep in mind there, that when you're looking at larger grain sizes, that indicates you need a higher level of energy in your system. So all this material needs to be compacted and then also glued together. And so we have cement material that we find in all our sedimentary rocks have cement. 3 of the more common ones that we see are silica, which is basically just quartz, calcite, and then hematite, which is an iron oxide. These 3 can actually be differentiated pretty easily with some simple tests. The hematite in many rocks will tend to be kind of reddish, and we'll explore that a little bit more with our next video on sandstones, because there's a lot of sandstones that have red or variable amounts of iron oxide in them as cement. But calcite can also be a good cementing agent. And remember, calcite is calcium carbonate. And so one test we use to see if calcite is present is we use these fun little dropper bottles of dilute 10% hydrochloric acid. And if you don't have this available, I believe you can use vinegar as well. It's a little bit weaker, but it should elicit the same sort of reaction. And so just as an example here, just maybe looking at this rock here, we can see that these grains, these clasts here, are cemented. If I can zoom in a little bit here, are cemented by some of this white material here. And so one way we would maybe test to see if this is calcite or silica, because they can both present themselves similarly, maybe kind of in a whitish, as a whitish material in between the grains or the clast. But we can test that with the acid here and put a drop on it. And sure enough, you can see the strong reaction you get there which indicates that this indeed is calcite that's cementing the grains together there. So this rock has a calcite cement, and if we come over here to this one, let me zoom back out just a skosh here. This clastic sedimentary rock, if we hit any area between the grains here with this material, with the acid, you can see nothing, right? There's no reaction at all. So that's telling us that this rock and this material lacks the calcite. So some common cement types there for you, and ways that you might be able to identify them. Remember that when we look at any sedimentary rock, especially the classic sedimentary rocks in particular, when we look at the types of material in the rock, so in this case the gravel, when we look at what actually those gravel particles are made of in terms of their individual rock types, that helps us figure out the source area, or what we sometimes call the provenance. And so what that means is if, for example, I have a conglomerate made out of rock particles that are all little broken chunks of granite, well, that would mean then that the source area, the region that was feeding the sediment into the system that transported the gravel, was dominated by granite. And so by looking at the composition of the particles in the rock, we can start to make some inferences and some interpretations about what the source area was. What was the area that was feeding the sediment into the system that transported the gravel? When you think about, though, you have to consider how old your rock may be, because you have to remember that landscapes are somewhat ephemeral. They're not maintained over time. So just because you have mountains and valleys in a landscape today doesn't mean that those same mountains and valleys existed anciently during the time that the rock, that sedimentary rock, was being deposited and formed. And so you have to sort of the further back you have to go, the trickier that may be. But nonetheless, that's something you can think about and something to consider. And so we're going to mainly focus on conglomerate and breccia, which are the two dominant rock types in this size range of classic sedimentary rocks. And these are dominantly differentiated by the clast shape. So even though they both contain gravel-sized particles, the way we divide these two names and classify these rocks is by the shape of the clast. So let's go ahead and jump into it, and we'll kind of jump back and forth between some notes and some things to give us some context and information, and then I'll show you some actual samples here as well. So conglomerate, let's start with this one. Conglomerates are clastic sedimentary rocks, again, made dominantly out of gravel-sized particles, but the shape of these grains is going to tend to be kind of in the well-rounded to subangular range. And I would encourage you to go back to my last video on introducing sedimentary rocks for a better discussion about rounding and clast shape or grain shape in these types of rocks. So whenever we see that the shape of the grains or the clasts in the rock tends to be overall in this range from quite well rounded to more to subangular, that's going to allow us to classify that as a conglomerate. And when we see that type of shape in the rock, remember that indicates that the clasts were transported over some distance, or possibly that they've been reworked. And let me explain both of those. So possibly those grains were banging into each other. They've collided as they've kind of worked their way through a river system, or whatever mechanism of transport was taking place. And so typically the more collisions take place between the grains, that's going to break off the little sharp corners of the particle, and it's going to tend to become more rounded over time. Reworked means that we might have an environment where there's a constant energy source, but we can constantly kind of move the sediment around and cause those collisions. So a river would be a good example of this first one here, but reworked, we might think of something like maybe a beach, right? So here's the ocean, here's kind of the waves coming in at the ocean, here's you up on the hill kind of watching everything taking place. And if we have maybe a big rock here, a big particle, a big boulder, if you will, on the beach, as the waves come in and cause the boulder, or maybe the grains, maybe that's a better example, use the smaller grains here. As the wave energy keeps moving the boulders around, smashes the sand grains into the boulder, over time what we'd expect to see is that all these grains no matter what their sizes are, would tend to become a little bit more rounded over time. So the wave energy causes them to be reworked over time. So we're not transporting the sediment very far. It's staying in the same place for the entire time. But because we have a constant supply of energy here with the waves in the ocean, we're able to change the shape of the particles. And that's one idea of what we call reworking the sediment is. So some possible environments we might see associated with conglomerates, and this by no means is an all-inclusive list, but just some ideas here. So you might see streams where you oftentimes, even today, see very rounded particles of sediments from all the collisions that take place. Alluvial fans, which is similar to a stream, is a place where we have mountains, a stream system in a canyon in a mountain that flows down to the valley and deposits a big kind of fan-shaped material on the valley floor. Maybe debris flows, which is kind of a slurry of sediment and water, usually precipitated by a heavy rainstorm event. And then beach, kind of like what we talked about right here with the wave action. Again, there might be others as well, but this is just sort of a few I chose there. And then remember that with conglomerates, and in the breccias too as well, that the clast or the gravel particles we see are going to tend to be favored by the hard rock type. So the harder the material, if you think about these particles being banged into each other, whether it's a beach environment or a stream or an alluvial fan, that's going to tend to break down and bust up the softer, weaker rocks, breaking them up into smaller and smaller particles. And so kind of it's a case of only the strong survive, right? The largest particles we're going to tend to see are going to tend to be harder rock types, maybe a quartzite, maybe quartz itself, maybe granite, maybe a metamorphic rock, that sort of thing. And then last thing here before we look at a few rocks, a few other names you might see out there that are kind of fun, that might show your advanced geology knowledge to your friends. This one doesn't have a whole lot of use, but you see it in the literature here and there. Conglomerate. So basically it's a conglomerate where the depositional environment is an alluvial fan system. And so we sometimes call those fanglomerates. Kind of a fun name. And then a name that mainly I think is used in the UK, although you see it here and there in other places as well, but I believe it has its origin over there in the UK. It's pudding stone, and pudding stone is typically kind of rounded pebbles, so a little bit smaller, something kind of in this size, maybe like coin size or marble size, but then it's surrounded by very, very fine sand and mud. And usually the colors of each individual clast are a little bit different. And so the idea is it kind of looks like, like a pudding, like a raisin pudding or something like that. Okay, let's look at some different samples of conglomerate to give you just some idea of some of the characteristics that are consistent, and then also some of the variables as well. Let's maybe drop into this sample here and take a good look at it. A couple of these rocks out of the way. So we can see with this sample here that we've got some clasts, again, gravel-sized particles, overall pretty rounded. So some are a little bit more oval shaped, like this one here on the right. Others are a little bit more spherical. But we can see that as we look at the edges of each individual class, they tend to be quite rounded, lacking any angularity or sort of sharp corners on them for the most part, right? You might find occasionally in any conglomerate the odd angular clast, but for the most part, all of these gravel-sized particles in here look to me like they're pretty well rounded. And they also look like they're composed of mainly the same material. It looks like they're all pretty much this kind of whitish quartz in here. Let's look at a couple other ones. Here's this kind of bigger one we looked at previously. And so we can see, again, particles, maybe some degree of variation in particle shape, but mostly in the rounded to sub-rounded, maybe a few that are subangular, like this one over here has got kind of a, some nearly 90-degree corners to it, but a little bit of rounding right there. But for the most part, these particles tend to be pretty well rounded, so that would help us and increase our confidence in calling this a conglomerate. We can see some different colors in here. So this has variable class types or composition. There's kind of the view from the side. Again, different colors in here. So that indicates it's got a diverse source area. Whatever sort of environment and area was feeding sediment into this system, probably a stream, had rocks of more than one type that were being shed off and eroded and put into that sort of system. So we've got that one there. That one had the calcite cement. Here's one with quite a bit of variability to it in terms of color, class, composition. So we can see a lot of different colors in here. Excuse me. But also class shape, right? So as we look at this one, we can see that most of the particles look like they're pretty well rounded, but you might be able to pick out a few in here where they're a little bit more angular. We've got one here that's, although we can't see all of it back in there, it's kind of stuck in there. And then of course, as you look at some of the smaller particles, you might be able to see maybe some more angularity as we kind of zoom in here to some of these smaller particles. But remember, because we're classifying it based on the largest class size, we're going to focus on the larger material, the gravel size material, and we're going to kind of ignore, for the most part, some of these little pebbles. So there's like a little cute angular particle in there. But by and large, you want to kind of get a feel for the overall nature of the sample and what it's showing you. And I feel really good with this particular sample in seeing how many of these particles are pretty rounded and calling this a conglomerate as well. Remember, the big difference between conglomerate and breccia, conglomerate tends to be a little bit more all-encompassing term than breccia. A breccia has a little bit more strict definition that needs to be met in order to call it that. So the conglomerate's probably the bigger umbrella term that we use. So lovely sample there. This is a Pleistocene conglomerate from northern Utah. I think this was from Ogden Canyon. A couple other ones here real quick, and then we'll look at breccias. This particular sample has a kind of almost baseball size clast in it, pretty rounded as we look at sort of the edges of it. Another somewhat rounded particle here, although it looks like it's kind of broken this way. So, and then as we flip it over, we can see again some of these very rounded clast shapes as well. So very, very textbook example here for the most part of a nice conglomerate. And then our last sample over here, I'm gonna move these out of the way, is this one, kind of a larger one. I'll zoom out a bit. And we can see with this sample that it's mostly made out of the same material. So we've got a lot of, again, these quartz particles in here. And as we look at their shapes, they, again, are mostly rounded. Some of them might be a little bit different. You can see a little bit of a point on that one there. But by and large, most of the shapes we see in this are indeed at least rounded to sub-rounded, with a few subangular ones in there. So this is actually a Cambrian conglomerate. So, okay, let's move ahead and look at breccias then. So a couple notes on our next rock type before we look at some samples here. So breccias. Breccias are going to, there we go. So to be a breccia, you've got to have clasts that are definitively angular. So these are going to have sharp corners and edges, so an angular to very angular in shape. And by having this type of shape in the class, that indicates that these particles have not moved very far. There's been little to no transport of these particles, or possibly that there's been some process that actually has crushed existing rocks and broken it into angular particles. There are, you might move the particles maybe in a stream, but you can't move them very far, because the further you move those particles in an environment like a stream, the more likely they are over time to become more rounded. And so we need either very little transport to none. A lot of times breccias will be deposited or emplaced in as one mass, so like one process that kind of lays them down in one fell swoop, if you will. And then there's several different types. The term breccia is actually used kind of across the board and in a variety of contexts. So we're focusing mainly on sedimentary breccias, which are going to be associated with sedimentary processes. So transporting sediment like in a landslide or other mass wasting event might be a very short duration and short distance flash flood. Could be collapse of a sinkhole that causes the particles to be broken into angular particles and then cemented together. But also breccia is a term that we see and use sometimes with volcanic processes, because volcanic processes can also fragment rocks into angular shapes and cement those together. And so we'll look at one example of that. We tend to stick these in with the igneous rocks because of their volcanic context. Impact breccias are going to be where we have meteorite impacts or other extraterrestrial bodies that slam into the earth and fracture and shatter existing rocks. So impact breccias are another way we might see this term used. Fault breccias, this is going to be where we have a movement along a fault. So the rocks are kind of grinding past each other, and as the rocks move across the fault, they'll tend to get busted and shattered and broken into angular particles and not transported very far. There's also processes where we have hot water moving through rocks and under pressure that can fracture and break rocks apart and turn them into breccias. And then a fun word you might see out there, this is always fun. Anytime you put mega in front of something, it always, it's going to get more attention than anything else, I suppose. So there's also these things in the literature called mega breccias, which are basically huge clasts, typically over 100 feet in diameter. And a lot of times you can't even see the individual particles unless you're in an aerial view from above. So you might see some of those examples as well. So let's look at a few different types of breccias. So let's start with this one here. This is a nice breccia with, looks like mainly quartz particles. But again, as we zoom in and look at the shape of the particles, we're not seeing a lot of rounding. There's a lot of little corners, edges, 90-degree or less or more, I suppose, but like these sharp angles in the particles here. And so this would be a good example of a breccia. And then, of course, the idea is that we'd have to start to figure out, using other clues that we can hopefully gather, what kind of process is responsible for this rock. So this is all one rock type. It looks like all the clasts are all quartz. So we sometimes call these monomict. In this case, this would be a monomict breccia. It's all one class type, versus if these were all different rock types, it might be called a polymict breccia. So there's a nice example of a breccia there. Here's a fun one because the rock itself, the sample, is quite rounded, but remember, that's not what we're looking at. We're looking at the individual particles within the rock. And as we look at these individual particles, we can see the very angular nature and sort of the broken appearance of this material that would lead us to call this a breccia. So this would be another really good example of a breccia. A little bit on the bottom there as well. Here's another fun example of a breccia. Again, look at these just, very sharp corners, right? If we transported a sediment of that shape in some sort of system, those little sharp corners would tend to get broken off. Here's one with like kind of a sharp point to it. Plenty of angular, odd shapes in this sample here that would lead us to call it a breccia overall because of the angular to very angular nature. I thought this would be fun. Here's actually a core sample. So this has been drilled out of the ground. I had actually looked at this one. I thought I'd call it, this one might be a tricky one as to whether you call this a conglomerate or a breccia, but this is a good example of just kind of what we face in the real world. Because if I kind of look at this clast here and its shape, I'd probably call this it's sub-rounded to subangular, but that would put, if just based on this one class, I would put it in conglomerate group. But if I start to look at some of these other class, I'd say that they're more in the angular kind of category, which would tend to sort of bump me into breccia. So realize this conglomerate to breccia thing is kind of a spectrum, right? And so there's one that's almost a perfect triangle. So my 2 cents on this sample would be to call it a breccia, but I certainly wouldn't have too much of a beef if another geologist or some person wanted to call this a conglomerate. So it can get a little bit tricky, but I thought that'd be fun as a core sample. Here's an example. I might have shown this with the volcanic rocks, but an example of a volcanic breccia. This is a tuff, so this is all ash components in here, but you can see there's these clasts, mostly a pumice, that are somewhat angular in terms of their shape, little sharp points there. There's almost like a little little square in there. And so this would be an example of a volcanic breccia. So just using that same term, but applying it to volcanic rocks, or yeah, some of the igneous rocks we looked at. This is a great example here. This is actually a fault breccia. So this is the fault plane surface itself. It's incredibly polished. You can see it kind of reflecting the light there. This thing is as smooth as a countertop right here. And as we zoom in, we can see, you know, the large particles, but also some of these smaller particles, which are still in the gravel size range, most of them, are pretty angular. So this is a place where the rocks have been pulverized as movement along the fault has occurred during an earthquake. That quick movement of the rocks across the fault has pulverized the little particles here, grounded them up into angular particles. They're all glued back together. So this would be an example of a fault breccia, and you sometimes see these along faults. So couple of last things here. I mentioned this kind of odd word, so it's worth just spending a minute on this one. You don't see this a lot, but if you want to maybe go a little more advanced here, a diamictite is basically a term we use, this is a rock type, for a conglomerate that is extremely poorly sorted. So what we're looking at here is a conglomerate where the range of sizes with respect to the particles varies considerably. And I've got a pretty good example over here of, let me zoom out, of a diamictite. So what you can see here is we've got this, you know, again, baseball, softball size clast right here. And in this case, this one's rounded. But most of what we see in this rock is this incredibly fine-grained, muddy material. So we've got these tiny, tiny specks of mud, and then occasionally we get these huge clasts as well. And so there's a huge size difference between these tiny particles in here and this one here. So this would be an example of extremely poor sorting, and the rock name that we would tend to use here would be a diamictite. So you might see that a little bit in the literature as well. And then the last thing I have for you, so if you're still with me and if this makes sense, or maybe this is all material you've known, and maybe you're just looking to take your knowledge to the next level, right? To impress friends and look like the smart person in the room at your next social function. Here's some adjectives you can add. So to the names conglomerate and breccia, and diamictite, I suppose, here's some names you could add to them as adjectives, right, to put in front of them. So one thing you might look at with your respective rock or sample is, are the particles mostly all touching? So notice here, we've got all the gravel-sized particles that all make contact with neighboring particles. If so, if the gravel tends to be the dominant portion of the sample, that's what we call a grain-supported rock. Versus if we have, maybe there's a few of them touching, like here or over here, but for the most part, there's matrix, or what we call the sandy, muddy, fine-grained material in between the individual particles. That would be what we call matrix supported. I'm trying to look at my samples here and see if I've got really good examples one way or another of either of those. I'm not sure any of them. What about this one? Yeah, I don't know. I don't think any of these are really over the moon great examples, but I think that the illustration would serve you just as well. So so you might say I have a grain supported conglomerate or matrix supported breccia. Another adjective you could add to your rock is the composition. So if the rock is dominated by one specific rock type in terms of the composition of the particles, you can throw that in front of the rock name to be a little bit more descriptive. So a chert breccia or a quartz conglomerate, right? So conglomerate would be gravel-sized particles, mostly rounded, but all those particles are mainly quartz, right? So we might call this rock over here, I'd feel comfortable calling that a quartz conglomerate. Or this one here looks like it's mostly quartz. I'd call this a quartz breccia, okay? So some other modifiers you might use, you might look at the grain size in the sample. So even though we're calling it all gravel, remember in our last video, we differentiated between pebbles, cobbles, and boulders. Those are all sizes within, and granules, I suppose, are all sizes within the gravel designation. So if it's mainly cobble-sized particles, kind of like, maybe like softballs and bowling balls, you might call it a cobble conglomerate. Or if you had a breccia, they had mostly smaller particles, maybe, I guess, like marble size or something. You could call it a pebble breccia. So there's just ways to be more descriptive. And then if you want to just go like crazy pro level, you can throw them all together, right? You can say, well, I've got a matrix supported limestone cobble breccia, or a class supported chert pebble conglomerate. So you can try to impress your friends with any sort of string of adjectives you want there. So hopefully this was helpful. Just kind of a review of some of these clastic sedimentary rocks, the gravel sized particles. Part of our series, Rock Identification with Willsey. Our next video, we're going to focus on sandstones. And so we'll kind of take it from there. We'll look at some different types of sandstones. Then we'll move on to shales and mudstones. And then we'll get into the biochemical sedimentary rocks, limestones, coal, chert, that sort of thing. So hope you enjoyed the videos. Appreciate everyone for watching, and have a great day.